Okay, so I think we can start.
Okay, thank you.
Okay.
Thank you very much for the invitation. So my talk will consist of two parts. In part one, I would like to give a brief review of a very old construction from the 80s. And in part two, I will report on new results. So let's begin. Let's fix some notation. So the base field is the field of complex numbers, and GLN is the general linear Lie algebra with a natural basis of matrix units. And we are interested in the universal enveloping algebra for these Lie algebras. And a stupid remark that there is no natural projection from this universal algebra to this one, which corresponds to smaller rank n. But there exists algebra morphism, some retraction, in the sense that it is identical on this subalgebra. I mean the, the morphism from this algebra, which is the centralizer of these matrix units, that is the subset, the subalgebra of elements which commutes with these matrix units. There is some natural algebra morphism from this centralizer to this one. So how to construct it, this projection? Let me call it canonical projection. The definition mimics the well-known definition of Harish-Chandra homomorphism. It's different, but the idea is very similar. So let's consider the left ideal in this algebra, universal enveloping algebra, which is generated by the matrix units from the last column, these ones. And likewise, take the right ideal, which is generated by the matrix units, which sit in the last rows. And then there is a simple lemma which says us that the intersection of our centralizer with this left ideal is the same as the intersection with this right ideal. And so this intersection is a two-sided ideal. And moreover, it holds that the whole universal enveloping algebra is the direct sum of a smaller algebra and this two-sided ideal. So we define this projection as the projection on this component. And this is an algebra morphism because here we have a two-sided ideals. This is the definition of the projections. And now I come to centralizers. My notation, which I will use throughout the whole talk, is as follows. Fix some number d, which has to be between 0 and n, some natural numbers, and consider a subalgebra denoted as follows, which sits inside GLN, and is defined as follows. We represent our matrices from GLN as by 2 block matrices and take this lower right block. In other words, it is the linear span of a matrix units satisfying this inequality. And this algebra is evidently is isomorphic to GLN of rank n minus d. Now the definition, the notation which I will use is as follows. We take the centralizer in our algebra, the centralizer of this subalgebra, and let's use this shorthand notation to simplify this complicated expression. And now our canonical projection give rise to a chain of projections starting from the minimal possible size of n. And we have this chain of projections, and it turns out that our projection are well defined as maps from one centralizer to another centralizer. The next remark is that these homomorphisms are consistent with the canonical filtration in the universal enveloping algebra. And so these are morphisms of filtered algebras. And by the very definition, we form the projective limit of all these objects, of all this filtered algebra, which is taken in the category of filtered algebras, which meaning that an element of our limit algebra is a sequence of elements from these pre-limit objects, and such that this chain of elements is consistent with the projections. This is the first condition. And the second condition is the compatibility with filtration, which means that the degree is bounded, the degree is preserved. And as a result, we get a filtered algebra as the limit object. Well, so let's take first the d equal to 0. So what is this centralizer? In this case, our subalgebra is the whole GLN. And so we have a centralizer of GLN inside the universal enveloping algebra, and this is simply the center. So in the case as d equal to 0, this object, we have a chain of projections, some quite natural projections, which relate the centers of our growing enveloping algebras. And so the limit object, this limit object, is a projective limit of the centers. And it can be identified with the algebra of symmetric functions. In fact, it's better to treat it as some related object, which is called the algebra of shifted symmetric functions. But anyway, it is isomorphic to the algebra of polynomials of countably many generators of growing degree, one generator in each degree. Okay. And now the following result holds. Let's call it the splitting theorem. Let's fix some d, which is now a positive natural numbers. And what is the structure of this limit algebra? I mean, this one. It contains, I forgot to say that we have also a chain of embeddings like this. So in particular, this commutative algebra is contained in each limit algebra A sub d. And it turns out that the structure is as follows. There exists some splitting. This algebra splits into a tensor product of two subalgebra. One is this commutative algebra, isomorphic to the algebra of symmetric functions. And the other is some object which turns out to be the Yangian, namely the Yangian, which corresponds to the Lie algebra GLT. There exists a whole theory of Yangians attached to simple Lie algebra, GL is not simple, it is reductive, but nevertheless, the Yangian of this algebra does exist, and it is actually the simplest member of the whole Yangian family. Maybe it should be viewed as the most fundamental, the most elementary object. So this object appears here from a different point of view, different with respect to the general theory which was created by Vladimir Drinfeld. And now let me recall the structure of this object. What is this? By the very definition, I repeat it, element x of the projective limit is a sequence of elements which are in the pre-limit algebras. And these sequence of elements are subject to two conditions. One is compatibility with the projections, which is means, and the other condition is restriction on the degree. It should be bounded. So we have some chain of elements by the very definition of projective limit, and this chain defines some element x of the limit objects, and it is related to these elements by projections, which I call pi sub n. And so the nth member of this sequence can be viewed as the image of our x with respect to this canonical projection, which, I repeat, exists by the very definition of a projective limit. So, to specify some elements of a projective limit, it's enough to specify this pre-limit object. And so the generators of the Yangian can be specified by indicating the images in the pre-limit objects, I mean the centralizer of finite dimensional Lie algebras. Okay, so now we have two kinds of generators of our limit algebra, I mean this one. First, we have generators of this commutative subalgebra, which is in the center in this algebra. It is in the center because it's commutative. And next, we have another family of generators of growing degree. The upper index indicates the degree, and the lower by indices are subject to these relations, just as for the matrix units of GL. D. Now, how to construct? The idea is as follows. Let's form this object. It is what it is. It is an n by n matrix, and the entries are matrix units. So this is object. It belongs to the tensor product of our enveloping algebra and the matrix algebra. And it can be viewed also as follows. The sum of the tensor products of the matrix units, which are viewed as elements of enveloping algebras, and another copies of the same matrix units, but they are viewed as elements of a matrix algebra. So there is some difference between them, and so I use script letters here to indicate this difference. And now let's consider raise this matrix in some power, say m, and take its trace formally as the sum of diagonal entries. And what we get is this multiple sum. We have m indices, a0, a1, so on, ranging from 1 to n, and we take the summation. This is the same as taking the trace of this matrix. And it turns out that these elements belong to the center. This construction is well known. It was, I don't know who invented it, but perhaps this discovery maybe is essentially due to two mathematical physicists, Perelomov and Popov, because they did in the 60s a remarkable work where they computed the eigenvalues of these central elements in finite dimensional representations and obtained the so-called Perelomov-Popov formulas. A very remarkable result. But this matrix was used by many other people also. So it may be difficult to say who really invented it. But now let's generalize a little bit this definition. Namely, now this by index will appear. We take the same power of this matrix, but take not the trace, but this entry. This means that such an element again can be written as a multiple sum like this, but the difference between this expression and this expression is that we fix the initial index and the last index. It is equal to I and j as here. And this element is no longer in the center, but if I and j satisfy this restriction, it lies in the centralizer of our subalgebra, this one, because of this restriction. It's quite natural because this subalgebra lies here and the indices are taken in this shape. Okay, so these are our tools to construct the generators. And now how to construct the generators? I repeat, you have to specify their projections, And the idea is as follows. Consider this object, 1 minus our matrix divided by this quantity, raised to power minus 1, so we want to invert it, and take the trace. And what we get? We get this element, I mean, this one, times some lower degree terms, which are the elements of the same type with the same ij by indices, but with smaller m, and with some coefficients which depend on capital N. And likewise, to get the generator of the second type, we do essentially the same, but not the trace, by taking the entry. Let me explain a little bit what means extraction with this coefficient. This expression can be viewed as a formal power series. We expand it into formal power series and then replace, then we shift our variable by n. And let me remark that this is a well-defined operation, because if you have a formal power series in U, it's impossible in general to shift, to make such a shift. But if you are dealing with the inverse powers and formal power series with respect to inverse powers, it's possible to shift our formal variable by a constant. So this is meaningful. And what we get now now we have that our commutative subalgebra is freely generated as a commutative algebra by these generators. And the Yangian part is generated by these elements, subject to some additional relations. So this is a highly non-commutative object. And now I come to the description of the defining relations of a Yangian. Turns out that the relations are essentially quadratic, but more precisely, they are quadratic linear because there are also some linear terms. In the compact form, the relations can be written as follows. So we have on the left some commutators, on the right we have some quadratic relations with the understanding, because m and n here can be natural numbers including 0, and we need to give sense to this expression. By definition, it is the Kronecker delta. A little exercise shows that this form of relations is actually equivalent to commutation relations for the generators. So when we take the commutator, it can be written as linear terms of such a type, plus some more complicated quadratic expression. So let me remark that the degree on the left is equal to m plus n, while the degree on the right is m plus n minus 1. So these are indeed commutator relations, which means, and actually we have an analog of Poincaré-Bergov-Witt theorem, which says that the associated graded algebra, associated to this filtration is commutative due to this property. The degree on the right is smaller. And actually, the graded algebra of a Yangian is a commutative algebra which is equipped with some Poisson bracket. And the Yangian can be viewed as a deformation or quantization of this Poisson algebra. The next topic I would like to point out is the famous RTT presentation of the defining commutation relations. It looks as follows: a very nice and compact form of writing the commutation relation, which is extremely useful in all work with Yangian. So the explanation: R is the Yang R matrix. Here, P is the permutation of two tensor factors. We have a tensor product of d-dimensional space, and P makes the permutation of the factors. And what is T of U? It is a kind of generating series of matrix valued generating series. These are the generators of a matrix algebra. Generator of matrix algebra. We form the generating series for our generators, again using the inverse powers, and form the matrix. And T sub 1 and T sub 2 means that we are working with here or here. This is quite well known, I hope, notation. And after all this manipulation, the infinite family of commutation relations can be transformed into a single matrix valued relation involving the spectral parameter. What next? There is another filtration. Let me call it a shifted filtration because the degree is shifted by 1. And let me discuss this topic, which can be called degeneration of our Yangian to some polynomial currently algebras. So for this polynomial currently algebra, it is the algebra of matrices with polynomial values, which depends polynomially with respect to some indeterminate x. The basis consists of a matrix units multiplied by powers of these indeterminates, which is can take values 0, 1, 2, but it's convenient to write it as m minus 1. And these are the commutation relations for these polynomial currently algebras. And there is a shifted filtration. Let's consider the shifted filtration in the Yangian, which is defined by proclaiming the degree of the generator equal not by m minus 1. This is meaningful because m is positive. And it turns out that taking the associated graded algebra, we obtain the universal enveloping algebra for this object, And the correspondence between the generators is as follows. To our Yangian generators corresponds this one. Roughly speaking, it is the top degree term of this element with respect to the shifted filtration. And how this appears, we remark that with respect to the shifted filtration, here the degree is preserved because the degree here is equal to m plus n minus 2. It is the same on the left and on the right in the linear terms. That it is smaller on the right, it is equal to this quantity. This means that in the graded object, all these complicated expressions disappears, and we get the universal enveloping algebra for the polynomial current. And another look to this construction is as follows. We can renormalize our generator by introducing the additional factor h, which plays the role of deformation parameters. And when this parameter will appear after renormalization, it will appear here, and as h goes to 0, it will kill this complicated part, and only this linear part persists. So as h goes to 0, we get the commutation relations for this enveloping algebra. So, in other words, the Yangian can be viewed in two ways. It can be viewed as a quantization of a certain Poisson algebra, which corresponds to the canonical filtration in the Yangian. But if we take the shifted filtration, we can represent our Yangian as a deformation of the enveloping algebra for the polynomial currently algebra. So this is the end of the first part. Maybe some questions?
Sorry, may I ask a question?
Yes, of course.
There are a couple of questions. First of all, I just wonder whether, what is the reference for the explicit formulas as far as this Poisson algebra you referred to is concerned? Is there any reference where this is explicitly written down?
But I'm sorry, the formula,
I said that Yangian is deformation
the formula
of
is
Poisson
the
algebra.
same. The formula is the same.
Just this. Okay, I see.
Only
fine.
the formula.
Oh, yeah, I see. So just wonder whether you can use some modern devices for deformation quantization of Poisson algebras to obtain Yangians. Then this will be the question.
Sorry, excuse me, repeat, please. What is the question?
I wonder whether one can use some modern devices, like, for instance, Kontsevich quantization formula, to obtain Yangian from this Poisson structure.
No, this is very simple procedure. We don't need the hard machinery of Kontsevich. Here, all is very simple and explicit.
Oh, I see.
So this is a very particular case. So we don't need to use some.
Well, I mean, Kontsevich machinery.
So this is a very simple result. Very simple.
Yeah, I understand, but you know, the advantage of using Kontsevich machinery, for instance, amounts in obtaining Duflo isomorphism in universal enveloping algebras from the scratch. Okay, and then there's the other question, whether what is, I know that universal enveloping algebras, they are co-algebras as well, they are Hopf algebras, and I wonder whether the way you obtain Yangians somehow relates with the co-algebra structures.
Yes, of course. But in my generalization, unfortunately, the Hopf structure disappears. So I have no coproduct, or at least I don't see how to define coproduct. So I will completely ignore this side of the story, the coproduct and the Hopf structure.
I see. Thanks.
It will disappear in my story.
Thank you.
Thank you. Let us continue.
Okay, so I come to the second part, which is generalization. So what is the general idea? So it's we can replace this concrete example, but some our possible choice of Lie algebra and Lie subalgebras. And what are possible choices? The most, I think, obvious one is to consider BCD classical Lie algebras. So we can take, this is shown in this table. And it turns out this is also an old story. In the 90s, this picture was worked out, and turns out that the centralizer construction, like this one, leads not to the Drinfeld Yangians, but to some other objects, which are called twisted Yangians, which are not Hopf algebras, but are Hopf ideals. And I don't want to explain on this, just only to indicate these possibilities. And the reference is Molev book and some paper by Molev and myself in Select Mathematical. And now let me turn to the recent work. The recent work is, the idea is consider chains of algebras and subalgebras of a different kind, of different structure. So as a first example, let's see what happens if we take as the algebras the direct sum of a certain number of copies of GLN. So take L copies of this algebra and take the subalgebra, take the diagonal embedding of GLN inside this, and next take the subalgebra in GLN, which is the same as before. So this subalgebra is the same as before, and it is embedded here by the diagonal embedding. If L is equal to 1, then we return to the previous picture. Now, the problem I would like to discuss is what happens if you take this centralizer. So here we have a bigger algebra, and the subalgebra is the same. And the question is what happens? And it turns out that some constructions, some results are extended smoothly and quickly. Some other results, which are similar to results which we know from the old centralizer construction, hold true, but the proof becomes much more difficult. Some properties don't hold. For instance, the property of the existence of a coproduct. I don't see, at least, I don't see if any reasonable definition of a coproduct. And there are some new effects which arise, because the situation is really different. So let me discuss step by step what happens. So first, the projections. Here, there is no problem. The canonical projections are defined in just the same way, again, mimicking the Harish-Chandra homomorphism. So we get again this chain of projections which relate our centralizers. And again, we can form the projective limit algebra. Let's denote it as follows by adding the parameter L, the number of copies that we take. And again, if L is fixed by this D is varies, we get embeddings. So in particular, the initial algebra, which corresponds to D equal to 0, is contained in each of these terms. So we have this embedding. And first, let's discuss what happens with this subalgebra, which corresponds to D equals to 0. And I recall this means that we can take the projective limit again in the category of filtered algebras of the centralizer of a diagonal GLN inside the L-fold direct sum of GLNs. The first remark is that this algebra is no longer commutative. This is quite evident because at the prelimit situation is not commutative, even if L is equal to 0. This is a very large centralizer. In some sense, it is responsible for multiplicities in the decomposition of tensor products of two irreducible representations of GLN. So there are large multiplicities which are connected with Littlewood Richardson coefficient. So this is a very complicated object. So this algebra is well defined, it's non-commutative. Now we have a generalization of a splitting theorem. So take D is fixed D, which is positive now, and let L is not equal to 1 by at least equal to 2. And it turns out, and this is maybe the main result, that there still exists a certain subalgebra, which I will call the Yangian-type algebra, which sits inside this limit object. And it is such that we still have this tensor decomposition, but it is not the tensor product of subalgebras, because we subalgebra do not commute. It is only the tensor product of vector spaces. So I would like to examine now what can be said about this Yangian-type algebra. It is not a Yangian, not at all, but I hope it merits to be called Yangian-type because it shares many properties, not all, but many properties of the Yangians. So the first question is about the generators. What happens with the generators and how to construct them? Now the procedure is as follows. We have to fix some alphabet in L letters. Let's denote this as simply by enumerate 1, 2, 3, and up to L. And let's take the set of all non-empty words in this alphabet. If L is equal to 1, we have only a single letter. And so there is a single word with M letters. But now we have many words. So instead of the upper index M, we have all words of length equal to M. So this object will replace the previous index M. And according to this, instead of this object, this generator, will appear a more complicated object, the generator, which is indexed again by index I and J, and also by a word of length M in our alphabet. And again, we have this restriction. And again, this will be some elements of our limit algebra, which is specified by similar elements, which with same indexation, but which depends on n and belongs to the pre-limit algebra, the centralizers. And so the question is how to specify them, how to construct them. And we can generalize the previous construction as follows. Take our matrix, which is composed from the matrix units, but you need L copies of it, which corresponds to L copies of our GLN. And it's convenient to deal with generating series. So these are our elements of a pre-limit algebra of a centralizer, which we want to specify. But to do this, let's use generating series with non-commutative free variables. So we need free variables instead of a single spectral parameter. We form, again, formal power series, but non-commutative, in inverse powers. And here there are possible repetitions, so we can have something like this one, and so. And to extract these coefficients, these elements, we have to do something similar to the previous construction, but we have to take again these shifts by n, but a more complicated expression. Again, we have to invert it and re-expand and take the ij entry of this matrix, and we, after that, we get some formal power series in non-commutative indeterminates and extract the coefficients which corresponds to some word, and we get these elements. And it turns out that these elements are compatible with the projections, with the canonical projections, and so they define some element of the limit algebra. So here are some little remarks. In the Yangian, we have a fixed number of generators. In each degree m, we have d squared generators. But in this situation, in the new situation, in our Yangian-type algebra, we have much more generators. And this number, as L is at least equal to 2, grows exponentially as m, the degree goes to infinity, which this means that our algebra is much more large, much more massive as compared with the standard Yangian. Now it turns out that there is no RTT presentation. At least I don't know how to discuss, how to find something which could replace the RTT presentation. This is a pity because RTT is a very powerful tool of working with the Yangians, but nevertheless, because of this, the proofs becomes much harder, but still one can prove many results, including the splitting theorem. Only the proof is more difficult, more tricky. And now what holds for defining commutation relations? The theorems can be stated as follows. So take two generators, but instead of m and n, we have two words, x and y. And it turns out that again, there exist some quadratic expressions on the right. So we again have some quadratic linear relations because some of these terms will degenerate to linear terms as before. So there are terms of the same type as before with some words which depend in some complicated way. I am unable at this point, I am unable to write explicitly these relations. I can produce an algorithm for computing them, and I can prove that they exist, but it seems to be complicated. There are some additional terms with a different structure of indices, not this one as in the Yangian, but with one. But again, we have the same type restrictions on the degree. So this is my notation for the length of the words, which corresponds to the degree of our generators. And one can prove, despite the fact that I'm unable at present to write explicitly the generators, I can prove that they exist and that they are defining relations. Next, one can again define the shifted filtration. And we have some degeneration as before, but the difference is that we get not a polynomial current algebra, but some non-commutative version of it. Non-commutative in the sense that instead of polynomials in one variables, we get some non-commutative algebra here. So let me explain what happens here and what is this algebra. So consider first the free algebra with L generators, and it has a basis which consists of non-empty words and also possible scalar terms. So we have to add the unity. And the product of words is the concatenation of words. So we just write one word after another. And it is a graded algebra. So the degree of a word is length. But we need something different. We need some modification of this picture. So I define it as F tilde. So we keep only the non-empty word without scalar term, and define a new product, which is not concatenation, but something similar but different. Let's call it pseudo concatenation. It is defined as follows. So we have two non-empty words, this and this one, and their product is defined as follows. Look at the last letter here and the first letter here. If they are the same, then we identify them. So we take this picture. So the length of this word will be m plus n minus 1. And if these two letters are distinct, the result is equal to 0. This is the definition. It's easily verified that this is an associative product. So we get some algebra, which is graded. Again, it is graded with the shifted degree. This is meaningful because we have a non-empty word, so this is non-negative number. And we can take the GL Lie algebra tensored with this non-commutative algebra. What is the meaning? There is no problems here. So we take the algebra of matrices, tensor it with, we can tensor it with anything, and we get some associative algebra, and then we convert it to a Lie algebra with a bracket given by the commutator. So this is a particular case of a general construction of tensoring GL with arbitrary associative algebra. So now introduce the shifted filtration by shifting the degree of our generator by 1. And the result is that if we take the associated graded algebra, we get the universal enveloping algebra for this object, which replaces the polynomial currently algebras. And again, one can modify a little this construction. So instead of taking the filtered deformation, we can take a deformation with some parameter h. Again, we can renormalize and letting h give, oh, sorry, this is not, this is absurd, excuse me. Not. So our Yangian-type algebra can be viewed as a deformation of this, one can say, non-commutative version of polynomial currently algebra, non-commutative with respect to this object. So this result is parallel to the corresponding result for the Yangian. So what is this mysterious algebra? It's not, actually it's not mysterious, because it is isomorphic to the path algebra on some keyword. What is this keyword? We take the keyword with L vertices and L squared arose, which corresponds to any ordered pairs of indices I and j, possibly equal to I to I is also possible. So this is the picture in the simplest case. L is equal to 2. So 2 vertices, 1 rows, this one and this one. And the path algebra is this algebra, this one. So the next topic is something which can be said about this algebra, which is not the Yangian algebra. This should be viewed for the viewpoint of the splitting theorem, which should be viewed as some non-commutative analog of the algebra of symmetric functions. I don't claim that it is in any way similar to the algebra of symmetric functions, but in our studies, it plays the role of the algebra of symmetric functions. So I recall what is this object. This object is the projective limit of the centralizers, the simplest centralizers. We take our algebras and take the diagonal subalgebra. D is equal to 0. And we have a canonical filtration, which is induced by the canonical filtrations of enveloping algebras. And taking the graded algebra, we get some Poisson algebra. And it turns out that this Poisson algebra can be described explicitly. It is very interesting and nice. I think a nice object. So take now not arbitrary words, but something different. Again, non-empty words in our alphabet, but circular words, which means that we put the letters on the circle with some order. Let me use the hat to indicate the circular word. So take one word. So I tried to represent this picture. Instead of letters, we can speak about colors. And instead of alphabet, we can say paint box of colors. So these are our circular words, which can be viewed as a necklace with the beads. The beads is our letters or colors. So the proposition is as follows. Our algebras, so I'm sorry, this is again some types. This is not our algebra. This is the graded algebra associated. It is commutative. Our graded algebra is commutative. It is the algebra of polynomials in countably many generators, but not as before indexed by 1, 2, 3, but now they are indexed by necklaces. The algebra of polynomials in the circular words or necklaces. And we can form the Poisson brackets between two necklaces. It turns out that this Poisson bracket is linear. So the result is some linear combinations of other necklaces. And because of this, the linear span of necklaces, which are generators, but the linear span is a Lie algebra. It is a known object. In the theory of keywords, it can be associated to an arbitrary keywords. It is called the necklace-Lie algebras. Let me explain its definition. So assume that we have two necklaces, okay, like this. And the Poisson bracket can be written as a sum over pairs of indices R and S, such that the corresponding colors are the same. So it remains to explain what is this quantity. It turns out that the picture is full. So consider our two necklaces and pick some pairs of colors which are of the same color, say this one and this one. So we want to explain what is the Poisson bracket, this part of the Poisson bracket, this one. And the definition is as follows. It is a difference of two necklaces, which are obtained by a kind of join of these two necklaces, by we can join or glue them in two different ways. One way is to remove this bead. And then when we go in this direction, we jump to this one, go and jump here and go in this direction. This is one summand, and another summand with minus sign is similar, only we remove this one. So we picture it as follows. So we jump here. And okay. So this is the description. And so we see, excuse me, that our algebra appears as again as a sort of quantization of a necklace-Lie algebras. But I have to point out that there exists a whole theory of necklace-Lie algebras associated to arbitrary cubes. It was initiated by Victor Ginsburg, by Bockland and Le Brun, more or less at the same time, independently. And our particular example corresponds in terms of their general picture to a special keywords, star of star shape. So we have one central vertex and L vertices which are related to this root by arose. So we have L+1 vertices. And there are papers about quantization of necklace-Lie algebras by Travis Shedler, Victor Ginsburg, and Travis Shedler. But it's unclear for me at this moment what is the connection between this general construction, their general construction, and my particular construction. And I have to mention that in their theory, the coproduct plays a very important role. But in my picture, the coproduct does not appear. But I have some generalization, actually. I have no time to speak about it. It is yet still unpublished. There exists some perpendicular generalization of necklace-Lie algebras. And finally, some final remarks. So what I would like to say that in principle, there exist other series of pairs of Lie algebra, Lie subalgebras, which admit the construction of infinite chains of centralizers. And the large n-limit transition is not a complication. It is actually a simplification, because in the limit, many things simplify. The structure of a limit algebra is simpler than the structure of a prelimit algebra. So in particular, if we are interested in the, say, representation theory of a centralizer, it turns out that in some situation, and in the case of Yangian, it is indeed the case, it's very convenient and useful to deal with the limit object and study its representation theory, and then obtain some results about representations of prelimit object as a specialization of a result which concern the limit object. So one can say one can look at finite objects from infinity. In this sense, it's useful. The next remark, I already said it, that the new Yangian-type algebra are more massive than the usual Yangians, and this is related to the emergence of free variables, of free algebras, or some analogs of free algebras, or maybe one can say some path algebras of some keywords, which are much more large objects. In the new examples, the nice RTT presentation seems to be missing, but despite this, we can prove some properties of Yangians and prove that they exist. Only it's more difficult. Another topic that I would like to highlight, that there appear some non-commutative, in the sense that the polynomial algebra is replaced by some non-commutative algebras, some non-commutative some analog of polynomial current algebras, but with non-commutative algebra replacing the polynomials. And it seems to me that there are some connections with keywords, some related constructions like necklace algebra and some other objects, double Poisson brackets, but they appear in maybe some other analogs of this construction. I tried to explain only the first example of it, but there are some other examples which, but there is many work to do in this direction, I think. So let me stop at this moment. Thank you.
Thank you. Thank you very much. Any comments? Any questions?
Yes, can I ask a question?
Yes.
Okay.
So thanks for the talk, very interesting. So you mentioned, I think, that you didn't also have a bi-algebra structure for these new Yangian-type algebras. Do you have something like is it something like a co-module structure, perhaps, that's possible?
No co-module structure.
No?
No bi-algebra. No.
Mm-hmm.
No. In the case of twisted Yangians, but this is a very old story. In this situation, it seems to be missing. No bi-algebra.
Okay, thank you.
Okay, any other questions? Sharagin, maybe you.
I already asked all my questions.
Okay.
Sorry for there are lots of questions, but actually I really need to think first before I can ask them.
Okay. Okay. Any other questions? Okay. Mikhail Arsenyevich not here now, but he was here. Okay, thank you very much. We can finish